Sorry.
Uh,
Sorry. Are we recording now? Recording later?
Sorry.
No, recording now. Just started. Go
So
ahead.
I should keep going. Okay.
Yeah,
So good morning, everyone, or good afternoon, depending on your hemisphere. Thanks very much, Mel, for the invitation to speak here. My name's Tim Trudgian. I'm a number theorist based here in Canberra. So it says on my talk there, UNSW, which means the University of New South Wales, down in Canberra at ADFA, which stands for the Australian Defence Force Academy. So in the US, there's three separate military academies. There's the military academy at West Point, the Naval Academy at Annapolis, and the Air Force Academy in Colorado Springs. But because the Australian Defence Force is at least one order of magnitude smaller than that of the US, maybe even 2 or 3 orders of magnitude smaller, we have them all in the one academy. So I have all my undergraduate students uniformed, and they walk around. They don't salute me because I'm nothing to them, but they salute all their colonels and air vice marshals and whatever. So it's kind of fun. I have my undergraduate students are in the military, but all my PhD students are civilians. So it's an interesting mix. Now, I should say, before the talk gets underway properly, I would advise, if you can, to change your screens to the maximum brightness. So what I'm endeavoring to do today is to give a talk based on some videos I captured a little while ago. I'll have a past incarnation of myself, who certainly was wearing trousers at the time. I'll have a past version of myself giving the talk, and then I'll provide some commentary over the top. So I've got around about 40 minutes or so of recorded talk to get through, but I'll stop every now and again. Questions, as we all know, is difficult for Zoom, but I will stop if someone asks a question. But I'll stop every now and again anyway, because perhaps the past version of Tim is a bit slow or doesn't explain something well or so on. So my goal is to play this video. There's no audio on the video, and I'll give some commentary over the top. So everything I say in this talk is about recent work that I did with Dave Platt. He's at the University of Bristol in the UK. We were talking earlier about accents. Bristol is in the West Country of the UK, so they sound not quite like pirates, but they sound a bit more R than the rest of the UK. So anyway, Dave's at the University of Bristol, and this is recent work which has appeared in the bulletin of the LMS, London Mathematical Society. It's talking about verifying the Riemann hypothesis up to a new height. So I have full confidence in the past incarnation of myself to know what he's talking about. So most of my talks will always start the same way. You know how it is. We play this game in number theory. We're going to have S as a complex variable, sigma plus IT. And when the real part of S, that is to say sigma, is bigger than 1, we can write the Riemann zeta function as this Dirichlet series. Of course, you can't write it when the real part of S is less than 1, or less than or equal to 1, because the series diverges. So not only can you write it as a Dirichlet series, but you can express it as an Euler product. It's the sort of thing we would give I don't know, first-year graduate students or whatever. Expand out the right-hand side, collect terms, use the fundamental theorem of arithmetic, and show that those two things are equivalent. Okay, so that's great. So that's for the real part of S bigger than 1. What about other values of S? Well, if you have other values of S, you can appeal to the wonder of complex analysis. You can use the superpower of complex analysis, the best superpower there is. And you can continue zeta of S analytically, or some people say meromorphically, dealer's choice, but you can continue it almost everywhere. And what do I mean by almost everywhere? Well, to the entire complex plane except at the point S equals 1. Because bad things happen to good people at S equals 1. We've got a pole of the zeta function at S equals 1. So I only have one diagram. Both past Tim and current Tim, and probably future Tim, all of us, we only have the one diagram between us. So what am I trying to draw here? Oh, very clever. What I'm trying to draw here is to say that here in the complex plane, this Euler product here, what I'm going to deduce from this is that there's no zeros to the right of sigma equals 1. Okay, why is that? If I give you a whole bunch of things, like a product of 6 things, none of which is 0, then its product can't be 0. And you might object and you might say, well, there's an infinite number of things. Okay, well, we could play some sort of uniform convergence games. But a product of non-zero things, the product has to be non-zero. So that gives me no zeros to the left of a line sigma equals 1. Sorry, to the right of the line sigma equals 1. Because I'm in the southern hemisphere, left and right kind of get confused sometimes. So I'm sorry if that happens again. But no zeros to the right of sigma equals 1. And then we have another device, a functional equation. I won't tell you what that is, but it relates points S to points 1 minus S. And that gives us no zeros to the left of a line sigma equals 0. And I say no zeros, well, that's true, but no zeros except these boring zeros, these trivial zeros. So we get zeros at -2, -4, -6, and at the negative even integers. So they're kind of interesting in a way. You can look at the Taylor series expansion. You can look at the Bernoulli numbers around there. It's kind of interesting. But in terms of encoding the information that we're going to care about in this talk, we're not going to bother about the trivial zeros. So for the rest of the talk, if past Tim or if this current incarnation of Tim says the word zeros, he and or I mean non-trivial zeros. Meaning what? Well, there aren't any zeros out here to the right of sigma equals 1. There's just the boring ones to the left of sigma equals 1. So everything else, the action, is going to take place inside the strip, sigma between 0 and 1. So sometimes called the critical strip. Everything in there is the stuff we care about. And I'm not going to write down what the functional equation is, except to say it's a way of equate. If you know zeta of S, you can plug it into some formula and get zeta of 1 minus S. Now, past him, if you notice, he was tapping the number 1 there. Unclear to me what exactly I was hoping to achieve. I think maybe displaying my arithmetic prowess, that I was going to number the pages in a normal cardinal order. So 1 and then 2. So we're off to a good start. So for the rest of the talk, I'm going to write rho to mean a non-trivial 0. And I'm not going to say non-trivial anymore. You know, we're old friends by now. We've talked about trousers and shaving and accents. We're all on the same page. So for a 0, I'm going to write it as real part beta, imaginary part gamma. And as I said before, the beta is going to be constrained to 0, 1. And in fact, you can do a little bit better. You can get rid of those endpoints. It can't be at 0 and it can't be at 1. It's in fact the prime number theorem. So the prime number theorem tells you that not only are they located within 0, 1, but you can't be on the boundaries of that critical strip. So what else do you know? Well, the zeros obey 2 degrees of symmetry. They're symmetric about the line sigma equals half. And again, I've only got one diagram. So it's the same diagram. I should just take a cardboard cutout of it with me to every talk. So what do I mean by symmetric here? Well, okay, there's the line sigma equals half. If you get some zeros that happen to be off the line, well, if there's one at, say, I don't know, pick your favorite sigma bigger than a half, like 3/4, then there's going to be one at 1/4. And they're also symmetric about the real axis. So if there's one up here, there's going to be a similar one with the same imaginary part, but flipped. So let's say 20 times I, there's going to be one at -20 times I. So in fact, if you got one off the critical line here, you get 4 for the price of 1, say. So because of this symmetry, everything that's happening downstairs is also what's happening upstairs. So there's no point considering what's happening downstairs. So for the rest of the talk, let's just consider the imaginary part being positive. There's none on the real axis, by the way. So let's just consider everything being, the imaginary part being positive. And you can't give a talk. A colleague reminded me, I keep forgetting that time differences are a thing. Of course, it's April 2 here, but it's April 1 where you fellows are. So April Fool's Day. Okay, I missed that. So you can't give a talk on April Fool's Day about the zeta function without mentioning the Riemann hypothesis. So I talk about these zeros being symmetric. Okay, that's fine. But not only are they symmetric about this line, but we expect them all to lie on this line, sigma equals a half. Okay, so that is the Riemann hypothesis, namely that all those zeros, rho, have real part, beta, if you like, equal to 1/2. So we're not going to talk too much about, there's thousands of ways you can attempt to prove the Riemann hypothesis, all of which seem to lead nowhere. But I guess what I'm trying to say with this cryptic remark at the bottom is it important with a question mark? No, it's not a question mark, it's a double exclamation mark. It's doubly important. And I believe this is my attempt at humor. I think the idea here is I've drawn a small margin in the side of the page, Fermat style. And I think lamentably the margin's too small for me to encapsulate a proof at this early stage. Very good. That seemed funny at the time when I recorded this talk during the height of the lockdown madness last year. So, okay, what I want to describe in the next 10 minutes or so is why anyone would care about the Riemann hypothesis, and more importantly, in terms of gearing up to my result, why anyone would care about a partial verification. So you might say, look, I care about a certain theorem, but anything short of proving it is dead to me. This doesn't mean anything. Well, so, okay, we can't prove the Riemann hypothesis at the moment, so you might say, well, what's the point of getting a partial proof? Well, somewhat remarkably, a partial proof does give you something, give you some crumbs from the table. So you can actually do stuff if you have a partial proof. So before I tell you why it's important to have a partial proof, I'll just tell you, briefly speaking, why you would care about it at all. So broadly speaking, if what you're interested in is the distribution of primes and other things, obviously that's a very fancy term. If you're interested in primes and other things, then you're certainly interested in the largest real part of a zero of the zeta function. Or that is to say, you're interested in the horizontal distribution of zeros of the zeta function. So there is an application later, we can talk about the vertical distribution, but for primes, all we care about is the horizontal distribution. So as an example, if I give you the prime counting function pi of x, counts all those primes up to x, well, we know the prime number theorem tells us it's asymptotic to the logarithmic integral of x. And what's that? Okay, it's the integral of dt over log t. Now also that's by integration by parts, that's asymptotic to x over log x. And it's reasonable if you say A is asymptotic to B. Okay, well, what's the error term? You know, A is asymptotic to B, so A divided by B tends to 1, but how quickly does it tend to 1? So when you look at this error term, pi of x minus li of x, that error term is expressible entirely in terms of the zeros of the zeta function. So if all you cared about was the error term in the prime number theorem, almost miraculously, well, not miraculously, but the only stuff that you really care about is the distribution of the zeros of the Riemann zeta function. And so I think what I'm trying to do here is to flesh that out. So what I'm writing down now is just what I wrote on the last slide. But such is the fun of doing things in a low-tech way. I recorded this talk, by the way, when our university was locked down. So I sort of snuck in one day and used the document camera. It was quite thrilling to break the law in that sense. So what am I trying to tell you? The Riemann hypothesis gives you what? I want to look at the error term now. I've got two things. A is asymptotic to B. Now, normally, you don't want to take the difference of two things that are asymptotic to each other. Like x is asymptotic to x plus 1. So the difference there is always 1. X is asymptotic to x plus sine x, say. You don't really want to be taking the difference because that could give you all sorts of crazy stuff. But still, you might want to say if something divided by something else tends to 1, how quickly does it tend to 1? So what is the error? What is the error in pi minus li? So if the Riemann hypothesis is true, the error is quite small. Okay, li of x goes pretty much like x. It goes like x over log x. So this is more or less the square root of that. So this error term is very small compared to, if you like, this main term. So pi can be well approximated by li of x with just an itty-bitty error term for any epsilon you like, say. So if the Riemann hypothesis is true, great. You know, that's a universe that I want to live in because the error term of the prime number theorem is plenty small. All right. Well, what if we're in some kind of horrible parallel Twilight Zone universe and the Riemann hypothesis were false? Well, one, I wouldn't want to do any more mathematics. I'd just send in my resignation papers. But if the Riemann hypothesis were false, what does that mean? Well, by definition, it means there's some zero with real part bigger than a half. Okay, so if it's got a real part theta that's bigger than a half, say, then what that means is that this error term is quite large. What does this omega here mean? This omega is the opposite of little o, meaning this side divided by this side does not tend to 0. So it's bounded away from 0. Infinitely often, there are values where this side divided by this side is bounded away from 0 by a constant, 0.01 or something. So the left-hand side divided by the right-hand side does not tend to 0. Or in layman's talk, this side gets as large as that side, say. So if there is a 0 off the line with real part 3/4, instead of this being nice and small, x to the half plus epsilon, this is quite big, roughly x to the 3/4. And of course, this could be, in principle, as big as, say, 1 minus a little bit, in which case this is huge. So all of a sudden, this as a main term isn't a great approximation anymore. The error term would be massive. So what we're trying to build up from here is an idea that if we're caring about just the distribution of prime numbers, the error term in the prime number theorem, then we're really interested in, can we rule out there being zeros which have a large large real part? So if there's a zero with a large real part, that's going to bankrupt us. That's going to give us this huge error term. So if I flip that around, then I want to live in a world where the real parts of the zeros are as small as possible. Now, it doesn't matter how clever you are. It doesn't matter where you went to school. It doesn't matter how many cups of coffee you had. You can't make the real part any smaller than a half. Because the functional equation means if there's one, take your favorite number that's less than a half, like 0.4. There's one at 0.4, then you've spit one out at 0.6. So you can't make them any less than a half. Half's as good as you can do. So in this mantra, if what we were saying is we want the real parts to be as small as possible, and a half is as small as you can get, then we're saying in some sense, and I use the inverted commas here, in some sense, the real parts being on sigma equals a half is optimal. Optimal, we'll come back to what it means with these inverted commas, but that is optimal. So in a sense, then the Riemann hypothesis is optimal. Optimal in the sense that the real parts couldn't get any better. What does better mean? Better means smaller. And that means the distribution of primes is as good as it could be. So yeah, I don't know exactly how we're doing, how we're going to do for time. Let me just stop here. I'll ask a quick question, and anyone who knows can answer. Just a quick question. Would you like me to finish at 50 minutes past, or an hour past, or an hour and 10 past? I don't mind, but
So talks are usually about an hour.
Yep.
But your talk is so enjoyable. If you needed a few extra minutes, that's fine.
Okay. That's very kind. No, I did indeed intend to talk. I did indeed intend to talk just for an hour, the academic hour, 50 minutes. But as I was looking for the Zoom link, I saw something which said the talks for an hour and a half. Maybe that was an old page or something. So I just wanted to be sure. So yes, I don't intend to talk for more than an hour. So what I've done here is I've said, I'll play. This is a classic way. We've all done the thing where you chair a session at a conference and no one has any questions and it's very awkward. So to combat that, this is a way to plant a question. One could ask later, if there's time, what do I mean by this optimal? And it's kind of interesting. What do we mean by it's almost optimal for the primes? So there's a way to get back to this, and I think I circled that slide, page 3, to say that if you wanted to ask this question, you could come back and ask about the PCC, the pair correlation conjecture, on slide 3. But okay, that's all on one side. So what's the point of the first 3 slides? Is to say that the Riemann hypothesis is important. Okay, well, and birds go tweet, right? But okay, we're all on the same page now. Riemann hypothesis is important. All right, and of course, it's worth $1 million. So there's 10 to the 6 reasons for studying it. It's unclear to me, almost certainly that $1 million Clay Prize in US dollars, which is even worth more in Australian dollars. So it's even worth more of my time to study it. What a bargain. So the Riemann hypothesis is important. Well, that's great. Now, as I said before, it would be nice if I'm going to say to you that I've proved the Riemann hypothesis to some high height. It'd be nice to say that I can get something out of that. So as a good second best, think of X as being large, say. If you know the Riemann hypothesis up to some large height, then you're in good shape. What do I mean by know it up to some large height? I mean, take X to be like, I don't know, 1 million. If I know that all the zeros row with imaginary part between 0 and 1 million, say, lie on the line sigma equals a half, that is to say, all the zeros up to height 1 million obey the Riemann hypothesis in that range, meaning they're on the half line, then I'm in good shape. And the higher the X is, the better. Now, I'm going to try to tease out the link of why higher is better. I mean, obviously, higher isn't going to be worse, but what can you do with that numerically? Why would you care? So, why would you want the Riemann height, or the height, to be as high as possible? Well, you could consider the Chebyshev function, psi of x. This is the standard thing we want to play at. We want to consider the Chebyshev function, psi of x. So what's that? It's a double sum. It's a sum over prime powers. All those prime powers less than x. So what you do, we've all played this game before. You take your m to be 1, so you're summing up the primes with weight log p. And when you take m to be 2, you're summing up the prime squares to log p and so on. And at some point, m caps out, because if m is too large, then you don't get any prime powers in the sum. So it's a double sum. Or you could write it, if you like, as a sum of the von Mangold function, if that's of interest to you. But okay, this is going to count primes with some weight and also prime powers, but there aren't that many prime powers, so we're not going to worry about them too much. But why would we consider this? Well, this is a very easy way then for us to tease out the expression for the prime number theorem. So the prime number theorem could equivalently be recast as psi of x is asymptotic to x. Okay, well, if I write down, if I'm going to tell you that A is asymptotic to B, as I say, I could do a lot worse and try to write down A equals B plus something else and hope to show that something else was small. So if I've just said, and this is all in all your, is all your standard number theory books, this is an equivalent way of stating the prime number theorem. Well, if I can do this, I ought to be able to write down psi of x equals x plus something, and then I ought to be able to show that something is small compared to x. So let's do exactly that. Psi of x is this, the main term, plus some small stuff. I'm not going to tell you what e of xt is. It's some really, really small error term. We could write it out, but you just consider it as being really, really small. So the thing here is to say psi of x is going like x plus some kind of sum over the zeros. It's a sum over the zeros, so x to the row over row, and we're going to chop that sum off after t. And you might say, hang on, what is this t? T doesn't appear on the left-hand side, but it does appear on the right-hand side. Oh, well, t is just going to tell us how good our approximation is. If we take t to be a bit bigger, we'll have more terms in the sum, and this error term will get a little bit smaller. But we'll just choose t to be whatever. Choose t to be some number. The idea here is that we can write psi of x as the main term x plus something, and we had better hope this something is going to be little o of x. We better hope this is going to be the error term, because that's what the prime number theorem tells us it ought to be. So we're going to recast the prime number theorem, if you like, in terms of this sum, and to say we want to see that that sum is little o of x, meaning that sum divided by x gets as small as you like. Okay, well, why do I care about the Riemann hypothesis to height h now? Well, if I want to approximate, if I want to evaluate this sum, I could split this sum up into two chunks. Okay, that main term ain't going to change. But if I know the Riemann hypothesis up to height h, then I can write the terms in here with their real part. I've no idea in general what these real parts are going to look like, but up to height h, I know all those real parts are dead on the line. And you might say, hang on, why have I done absolute value here? Well, because remember the zeros upstairs are the same as the zeros downstairs. So Riemann hypothesis up to h, if you like, is Riemann hypothesis from minus h to h. So for all those zeros up to height h, we know their real parts are half. These real parts, otherwise, they could be really close to 1. They could be 0.999 for all I know. So when we split this sum up, we're going to get two pieces. One where we know lots of stuff and the rest. So when we want to start to look at psi of x numerically, then in this sum here, we're getting a huge saving because the real part is a half and it's not some kind of random wacky number that could be arbitrarily close to 1, say. So this is going to be much, much smaller. These terms in here are going to be much, much smaller than the terms in general. I must say, past version of Tim, I've drawn a smiley face. I was trying to make some statement. I couldn't obviously figure out what I was doing, so I made a smiley face. That's great. What does that mean? That means that those terms are smaller, right? The terms in that initial sum are smaller because the real part is smaller. Okay, that's great. So we've got a main term plus a smaller error term, which we can compute. Yeah, take your favorite x, compute that sum up to h, and then use something else, use some other techniques. If we get time, we can talk about zero free regions. We can talk about all sorts of stuff. But the idea is on this sum in the middle, I'm getting a huge saving. And that's going to mean a big difference when I want to get explicit results about the number of primes at an interval, say. So here's that kind of one diagram I have with slight finesse. So I'm saying, say the Riemann hypothesis is true up to some height h. That means all the zeros lie on the critical line there. So think of your h as large. They all lie on this line. Well, then what happens after h? Well, crazy stuff happens. But I do know the zeros can't get too close too quickly because I know these so-called zero-free regions of the zeta function. They're pretty horrible. They go like 1 minus a constant over log t. So asymptotically, the zero-free region has width 0, but it means that the zeros can't get too close. They can't be under the shaded area here. This shaded area gets smaller and smaller, but they can't be underneath that shaded area. And somewhat miraculously, knowing that is enough to deduce quite remarkable information on, say, the number of primes in a short interval, for example. So Riemann hypothesis up to height h gives us a real boost. Gives us a real boost because numerically we get a huge improvement. And often it's the zeros low down that are contributing the most to these sums. So knowing that the zeros low down have real part equals a half is a great bonus. So, okay, a quick summary then of where we're up to so far. Zeros with large real parts are the worst. It's like if, you know, your friend pours you a glass of whiskey and he puts ice in it or something. It's just the worst possible thing anyone could do. So ice in your whiskey is terrible. Zeros with large real parts are terrible. They're the absolute worst. If what we care about is distribution of primes, we want those real parts to be small. So that means, I think I'm going to do three things now. And I think that I've said the first one, the Riemann hypothesis is important. Yeah, that's true. And what I've tried to highlight in the previous slide was that the Riemann hypothesis to some large but fixed h is also important. So that's what we did on the last page or two. So the higher the h is, if it's a million or a billion, okay, we're in pretty good shape. And here's a third one, which I think is interesting and which perhaps needs to be teased out a little bit more. So not only if I know the Riemann hypothesis to height h, but I know very accurately the location of the zeros. That's important. So that is to say, in point 2, that's just saying, like, take your favorite h, like 100, say. So I don't know how many zeros there are up to a height 100, I don't know, 5, say. So if I could prove that there's 5 zeros up to height h and they're all in the critical line, there are no others, all right, that's point 2 done. But the first zero is at, you know, a half plus 14.1, blah, 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 times I. But there are applications where I want to know that 14.1, blah, 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 to a very high degree of precision. So knowing the Riemann hypothesis up to some height is one thing, but I could ask for a lot more and say, not only that, but isolate each of the zeros up there to a very high degree of accuracy. So find out what that first zero is up to, I don't know, 1,000 places, say. So that's a third thing, which is often important for applications. So I want to take a short 5-minute digression to flesh out why 3 might be important, why you might want to know the zeros, at least the first, 10 or 1,000 or something, to a high degree of accuracy. So why do you want to know that? Well, you're going to be considering these sorts of sums. So if we're looking at the zeros up to height, I don't know, 1,000, pick some h that's reasonable, then it's going to be x to the 1/2 times x to the half plus gamma. Well, the x to the 1/2 can come out the front of the sum. So really what I'm looking at is this guy here. Now, these are a bunch of complex terms. X to the I gamma, x is a number like, I don't know, 1,000, a million or something. So these x to the I gammas, numbers on the unit circle. If I didn't know any better, I'd say I've got a whole bunch of things on the unit circle. They could be pointing this way, that way, this way, that way, who knows, kind of spinning around. At a first glance, I could just use the triangle inequality. Take the absolute value of the sum, that's at most equal to the sum of the absolute values. Okay, yes, we can pass pre-calculus 1, yes. So we know how to use the triangle inequality, that's great. And if I do that, I'd get an estimate on this sum. But almost certainly, I'm going to get a wildly pessimistic estimate because I've ignored all sorts of cancellation that could have happened. I could have zeros pointing this way, that is to say x to the I gamma could be that way, the next one could be over here, and by pretending that they all point in the same direction, by pretending that the triangle inequality is the best thing possible, I lose all of this possible cancellation that I have. So if I want to keep that cancellation in play, if you like, if we think about numbers around a complex circle, I need to know those angles of theta, say, around the circle. And the higher accuracy I know those angles to, the more precise I can make the sum. So if I know the location of these zeros to, I don't know, like 1,000 decimal places or something, if I know them to a high degree of precision, then I can do one of two things depending on the problem. If I want to make this sum very, very small, I could kind of rig the deck, choose a bunch of x's so that these gammas kind of line up using what's called Dirichlet's approximation theorem. You know what it is? Dirichlet's theorem for approximating irrationals by rationals. You know, we can choose a sequence of these values so that the cosines line up, say. So choose these so that these guys reinforce each other. Or I could rig the deck the other way and choose them so that they don't reinforce each other, so that they kind of cancel each other out. So if I am faced with a problem, like I want to say these sums can get big, these sums can have big oscillations, then I can rig the deck. If I know the gammas to a high degree of precision, I can choose a whole bunch of x's, like, I don't know, 1,000,000, 1,000,000,006, 3,000,000,002, or whatever. Choose an infinite sequence of x's and say, on those x's, I'm going to make these guys line up. So we're going to get much better than the trivial bound, much better than if we just smash everything with the triangle inequality. So this is kind of interesting in that this is how things like the Mertens conjecture was disproved. So when Tavrila and Orlitsko disproved the Mertens conjecture in the 80s, oh, you might object, past Tim is off the screen now. I'm sure if he knows what's good for him, he'll push the screen up. There we go. Okay. So very useful for things like disproving the Mertens conjecture. So the Mertens conjecture, any kind of arithmetic sum where you can relate it to zeros of the zeta function, you can try to prove or disprove it based on things like these oscillation results by rigging the deck, by choosing a bunch of these x's so that the imaginary parts reinforce each other. But in order to do that, you've got to know these zeros to high precision. So people like Orlitsko, all sorts of people have calculated these. Oh, there you go. I said it was also good for passing the long winter evenings. So knowing these zeros to a high level of precision is important. Why? Well, you can prove or disprove a whole bunch of conjectures based on arithmetic sums. You can examine the linear independence of the zeros. I mean, I've given a lot of talks on the zeta function. Always, I want to say this point. Take the first two zeros of the zeta function, like it's the first one's at a half plus like 14 times I, and the second one's 20 times I or whatever. Okay. Now, with any of those zeros, so little is known about their algebraic structure. Like just take the first one, say, it's not even known whether that number 14.1 blah blah blah. It's not even known whether that number is rational. I mean, presumably it's irrational, presumably it's transcendental, presumably it's horrible. But just like, say, Euler's constant gamma, you just got no idea whether that number is rational or not. Now take the first two zeros, say, it's not known whether there's any linear dependency between them, like maybe 1,000 times the first one minus 900 times the second one equals 0. So if I write them as C1 gamma 1 plus C2 gamma 2, and the C's are integers, apart from the trivial and boring one, C1 equals C2 equals 0, it's completely unknown whether there's some number with 10 trillion digits, C1, and some negative number with 10 trillion digits, C2, such that this linear combination equates to 0. I mean, presumably not. Everyone thinks the answer is no, but it's just impossible, just off the charts crazy. But if you want to make some partial progress and then do something with those results, those conjectures, the so-called linear independence conjecture, which everyone believes, if you want to do something with that numerically, then you have to know some of these partial results. And to know that, you have to know the zeros to high accuracy. So that's what I try to flesh out with this point 3 here, is that it is of use for people to know the Riemann hypothesis, not only to some height, but also to know the zeros to a high degree of precision. So, okay, there's the three amigos here. Riemann hypothesis is important. Now, I've said pause for questions. That's very astute of me, but I might keep going just because this is what slide is it? 5 or 6? So if you had questions on this slide, on slide 5 or 6, do ask me at the end, but we all know it's sometimes tough on Zoom to pause for questions, say. So, but anyway, those are the three things. Riemann hypothesis is important. Riemann hypothesis is important to some height h for the partial results. And if we also know the location of the zeros to high precision, then we're in good shape. So that's a background as to why anyone would be interested in a partial result. So these 1, 2, 3 things I want to flesh out again on the next slide. And now I want to tell you what it is Dave and I did in our work, and what the philosophy was, I suppose, why we wanted to do what we did. So, right, so those are the 3 problems. So first problem, Riemann hypothesis, that's still unsolved. Oh, it's April Fool's Day, but it's still unsolved. Okay, what a shock. It's still unsolved. But Riemann hypothesis up to height h, yeah, a lot of people have worked on that. Riemann himself, I think, would have proved, say, that the first 5 zeros lie on the critical line and there are no others, say. But in modern times, Riemann hypothesis up to height h, there's a nice result by Platt in his PhD thesis in 2011, and the paper was published in 2017 that gives Riemann hypothesis up to 3 times 10 to the 10. So that's a big number in anyone's books. And in the same sources, Platt looked at the accuracy of the zeros. So what do I mean by this cryptic notation? 0.3, remember 0.3 was Riemann hypothesis up to a large h plus the accuracy, so plus the location. In these same sources here, he does all those zeros up to 3 by 10 to the 10, and also isolates them to 100 bits of precision. So, you know, to accuracy of plus or minus 2 to the minus 102 or something. So all those zeros you can get to a very high degree of accuracy. So that's the state of play before Dave and I looked at this problem together. So, okay, what did I try to do? Yeah, okay, I guess I tried to prove the Riemann hypothesis, but that was too hard. So I moved on to something that was doable. Now, 3, you might say, well, that's a lot of zeros that we know to an awful amount of precision. Probably that's enough for any person on God's green earth. And that's true. There's no real need, at least no need that Dave and I can see, for any human to want to know more zeros to a higher degree of precision. Okay, and there's caveats and stars and so on we can come back to. But there's no need for any more zeros to be computed with a crazy high amount of precision. That's enough for every application that everyone has in mind. So if you like, 1's off the table, it's too hard. 3's off the table because there's no need. So what about 2? Can we forget about proving the isolating the zeros to a high degree of precision, but can we just prove the Riemann hypothesis to a very high height? And in a way, the point of 2, okay, I think I'm writing it down now. It's a bit tough remembering what I wrote a year ago, but yeah, try to improve this, right? So remember, I said 3, what's 3? 3 is proving the Riemann hypothesis up to some height, some large height, some new large height, and getting a high precision. Now, one of the reasons why that's so slow is that it takes you a long time to isolate the zeros to that high precision. So if you want to try to extend Dave Platt's 2011 and 2017 calculations, it's going to take an awful long time, because to isolate those zeros to a high precision, there's many drains on your time. That's a huge drain on your time. So in a way, you're kind of releasing the handbrake here if you say, now I just want to go up to zeros to some new crazy high height. I don't care about isolating them. I'm going to free myself from those shackles and say, we already have plenty of information about where they are to high precision. I just want to find one in any interval, like between this interval, say, I'll find one and I'll move on. I won't bother about finding out, is it within some interval of plus or minus 10 to the minus 3 or something. So as soon as I find one, I'm going to move on. So I'm going to kind of sacrifice accuracy. It doesn't affect the validity of the result, but I'm not going to store any information about the precision with which I locate these zeros deliberately, and that will allow me to speed through, plus with some other improvements. But that's the main philosophy of why you can go so much higher, because you don't care anymore about the precise location of the zeros. So my goal, Dave's and my goal, was to improve on 2. Oh, yeah, okay, so why do it? Okay, 1, it improves on other results. Remember, there's this quote by George Mallory. He's this fellow who climbed Mount Everest. Someone said, why are you trying to kill yourself to climb Mount Everest or something? And he said, why? Okay, because it's there. Because Mount Everest is there and it needs to be climbed. Some kind of pithy quote that you see on desk calendars and so on. So, okay, what's the Tim Trudgian equivalent quote? Why do I do this? What's my Mallory equivalent quote? Why? Well, the problem's there, but also, why do I do it? Because there's bills to pay. I've got a family to feed. I've got to do something with my life. So why do this? Well, it's a problem I can work on. That's why. So it improves on other results. That's why you do it. 1, you can do it. But 3, and I'll more or less end on this next slide. I want to put up another reason to do it, and I've written down there confusion. So slide 7, which I'll make the last one. Confusion, where it's surprising that there would be so much confusion. So in that, suppose you're working in an area that's not analytic number theory, excuse me, like in I don't know, cryptography or graph theory or something. Suppose you're in some area where you just want to have a figure, like I don't know, physics or something. You just want to know the Riemann hypothesis is true to this height. Good, I can put that in, and that can be, you know, a way to say some partial evidence for it. So you just want to figure. Somewhat shocking, I thought, when I looked through the literature, that there's no real agreement on what figure to use. I mean, Riemann hypothesis is pretty important, as we've tried to say in the last 6 slides. So why is it the case that I can't just point to something? Like I can point to, I don't know, the monster group or something and say, there you go, that's the largest finite whatever. I can point to that. I can get that Wikipedia reference and I can move on. But if you just try to type in, you know, what is the height to which the Riemann hypothesis is true, you're going to get like 20 different answers. So what's that about? So that's what this slide's talking about. Why is it that you get all these different answers? And because of this confusion, it seemed natural to try to sort of slay all that, put that all to rest. So Platt has this figure of 3 by 10 to the 10 in his 2011 thesis, and it was published in 2017. So that's one figure that does the rounds. But there's always other figures that you get them on Wikipedia or Math World or whatever. I mean, you find them in people's published papers. And you get all these other results that seem to be floating around. So one is by Sebastian Wiedenivsky, 2004. So this is 2.4 by 10 to the 11. So a little bit bigger than Dave's result, say. And another one by Xavier Gourdon, also in 2004, which is a little bit more. So it's an extra order of magnitude, 10 to the 12, 2.44 by 10 to the 12. Then there's another result buried deep within a paper by Franke, Buter, Kleinhung, and Just in 2017, giving 10 to the 11. But, okay, you might say, well, here are 3 things, 1, 2, 3. All of these numbers are bigger than Platt's. Now, hang on, why is Platt publishing his result in 2017 if we've got these better results in 2004? Why would anyone do that? Well, yeah, I mean, this is part of the confusion. In 3, for example, there's absolutely no details given at all. They just say, oh, and by the way, just on the side, we're able to do this. No details about how long it takes, and I'll come to it more importantly in a moment, no details about the errors that accumulate. Okay, so that's 3, 0 details given. There's some details given in 2 and 1, but 2 and 1 never appeared in print, so there's that. But also, not only do they not appear in print, but in both 2 and 1, and also in 3, the real problem is how you're going to account for these errors accumulating in the use of the fast Fourier transform. So the way that all these methods, including Dave's, by the way, the way that all these methods improve on previous methods done by people like my Australian colleague, Richard Brent in the 70s, people like Herman Tarila, and before them, people like Rosser and Schoenfeld and so on. So the way that these modern methods improve on those past methods is to use this fast Fourier transform. I only have, in order to keep to my own schedule here, I only have a minute or 2 to go. Briefly speaking, what I'm going to do is I'm going to try to sample the real line in a whole bunch of places. I'm going to use the intermediate value theorem to say if I have a function that's continuous, if I'm real valued, if I measure it here and it's positive, I measure it here and it's negative. So like that, say, then it has to be 0 in between. And that's how I'm going to capture a lot of these zeros. And the fast Fourier transform is a very clever way of employing that approach. So, but when you do that, there's an awful lot of zeros. There's an awful lot of transforms to be taken. There's an awful lot of errors that can creep in. And there's no hint of saying how, with all this data, with these trillions of zeros you're looking at, how any of that stuff's going to be taken account of. So what that kind of means is that many people were, even though this result was the smallest of those 3, many people were pointing to that result and saying that seems the most reliable. And don't take my word for it, take my fellow countryman's word, Terry Tao. Terry Tao writes a paper back in, I don't know, 2015 or something. and so did Harold Helfgott when he proved the Ternary-Goldbach conjecture. Both in their paper, they give many of these figures, and they say, look, who knows whether these are true or not? Like, I mean, I believe the Riemann hypothesis is true, so probably they're all true, but who knows whether these are true or not? The advantage of this one is that it's, if you like, deliberately slower, but it employs this so-called interval arithmetic. And you never know with computer calculations. It could be a cosmic ray or something that hits the computer and everything fries, or I could spill my coffee on it, or who knows what. Okay, but modulo all that. This is saying deliberately, I know after I've done an answer that I know after I've done a calculation, the answer definitely lies within here. And that's a fact. You can swear in a court of law on a stack of Bibles that the answer lies in this interval, say. And then all your calculations are done based on the answer lying in this interval and this interval. Then you add them together, you add the intervals and so on. Now, that's much slower than using regular floating point arithmetic, but is much more robust in that when you do all these Fourier transforms, you put everything together, you could actually keep track and again, swear on your, on your grandmother's grave or whatever, that you definitely know the answer's lying within there. So roughly speaking, what Dave and I did was we said, well, this is kind of crazy that there's no one result to point at and say, this is it, this is the answer. These things are all bigger than Dave's. In some way, Dave takes the moral high ground and his is more robust. Okay, but that's not really satisfactory. And how do you explain that to someone from, say, physics who just wants an answer? So we thought, okay, well, we're going to do this approach of taking the handbrake off, not looking at the zeros to high precision anymore. Plus, in his algorithm, in this paper and his thesis, there are some theoretical aspects in there, which is what I improved. There's some computational aspects in there, which is what Dave improved. So we improved, if you like, we pulled out all the stops in the algorithm, sharpened absolutely everything. We took the handbrake off and said we're not interested in the precision anymore, but we're still definitely interested in this interval arithmetic. And then we'll go as high as we can go before we lose interest in it or the supercomputer melts. And that height happened to be 3 by 10 to the 12. So Dave made his code available. So I think the paper, what's it called, like First View or In Press or something. Like you can find the paper on the bulletin of the LMS website. It doesn't have the page numbers, but you can find it there, and there'll be a link to his code, say. So the code's there, and we use an awful lot of supercomputing time. It's a very fast supercomputer here in Canberra. I can't remember the number of hours we use, a crazy number of hours over 3 human years, never mind the core years or whatever, 3 human years the calculation went on for. So the idea was to go sufficiently high, higher than all these 3, but still with this idea of robust interval arithmetic. The penalty, though, is that now we don't know anything about the precision of the zeros between Platt's height of 3 by 10 to the 10 and our new height. But as I said before, I don't think anyone needs to know that. And if they do, okay, well, they can do something else. They can do a very small calculation. If they want to know the first zero after this with some crazy precision, they can do that on their own. So roughly speaking, I'm going to stop there. I mean, I had another 10 minutes or so of slides to go, which just goes through the algorithm, but we don't have to worry about that. But the takeaway, I suppose, is 2 main things. One, what I just said on this page, we wanted to remove the confusion, the uncertainty, and have just one figure that people could point to and say, how high is it true to? It's true to that height. And that height, and I can swear in a stack of Bibles, that's true. It's bigger than all these other ones, that helps, but also it's got this robust interval arithmetic approach. And what's the other thing to take away? The other thing to take away is that there is actually some numerical use to be had by knowing the Riemann hypothesis up to some large height, because then when you do your sum over primes, one of those pieces you know to a much higher degree of precision. So when you're looking, for example, like you want to know, is there a prime in this short interval, say, like for graph theory or whatever, you want to construct some network and you want to base it on some prime and some interval, say. Well, you want to know that quite accurately. And one of the ways of knowing that is to estimate this prime counting function quite well. And as I said back on slides 4 and 5, one of the best ways of doing that is to split the sum up into a Riemann hypothesis part and an other part. And the higher you know the Riemann hypothesis part, the more information you have on that piece. So from a numerical point of view, knowing the Riemann hypothesis up to a high height helps quite a lot. There are many applications which we put a few in the paper. I'm not going to talk about them now. The paper's on the archive if you don't have access to LMS, but it's more or less the same manuscript. But there's some applications in there more or less that you get for free by plugging in this new height. So thank you very much. I appreciate that it's difficult. One, you have to contend with my accent. Two, you have to contend with past Tim, who may or may not know how to do his arithmetic or may think his jokes are funny and they're not. And three, you, like everything on Zoom, it's a bit interesting. You have to contend that we're not in the real room. So thank you very much for your kind attention. I'll stop there.
Thank you. Let's see. Can you unmute? This is to the world at large. And are there questions for Tim?
Yes, I have one. Perhaps it's kind of a philosophical one, but since you have thought carefully about these things, I'd like to get a little bit of your intuition as to how special this is for the Riemann zeta function as compared to other zeta functions, perhaps Dirichlet L functions, or even going farther away from this situation to something like Selberg's zeta function, where you know that the zeros are on the so-called critical line, but the question of precision it's not has not been explored. What's your intuition? Are we? Is there something perhaps that is very special about the Riemann zeta function, but may change for other zeta functions? I mean, you have gotten very close to the inside of this object, so I would be interested, even if it's just philosophical ideas.
Thank you for the question. I think first thing to say is that I don't think I've got any close to understanding anything. The more I read about it, the less I understand about everything. But let me take your question in a couple of parts. Yes, I think absolutely there's something special about the Riemann zeta function. But in terms of this method, this approach, this will work more or less for any L function you like. Let me just quantify that. How is it that we actually search for zeros? Well, we search for zeros by saying the zeta function is complex valued. It's going to be very difficult to look for a zero of a complex valued function because the real part and the imaginary part have to be zero simultaneously. That's tough. So what we do, step one, is to convert the zeta function into something else, sometimes called Hardy's Z function or Z function, say. Now, what's the point of doing that? Well, that's a function whose zeros coincide with the zeros of a zeta function, but also the Hardy function is real. So the whole point of doing that is that now we have another function. So now we throw the zeta function in the bin. We don't look at the zeta function anymore. We look at the Hardy function. Right, because if we find zeros for that, that's the same as finding zeros for the zeta function. But now the Hardy function being real means we can play this intermediate value theorem game. I'm going to measure the zeta function here and here. And if one of them is positive, one of them is positive and one of them is negative, there has to be a zero in between. So then we can play that same game for other L functions, like, as you say, Dirichlet L functions. And in fact, so I say in the abstract or whatever, this is all joint work with Dave Platt. I mean, it may as well be 95% Dave Platt. In his thesis, he does indeed look at Dirichlet L functions. So, for example, showing that, I don't know, take your favorite Q, like 4 or 1,000 or something, showing that the first zeros up to some high height, like 10,000 or something, lie on the critical line. So with and as you say, Dirichlet L functions of the Selberg class. So these some of these calculations are quite old. So Rumley did some work with Dedekind zeta functions. McCurley in the 80s did some work with Dirichlet L functions. And Kevin O'Brien, who I see in the chat, he's obviously written papers and knows plenty more about some of that stuff than I do. But the idea here is that with any L function you like, so long as you can play this game of replacing it by a Hardy type function, a function that shares the same zeros but is real, then you can play this approach of hitting it with a bunch of points and sampling whether it's positive or negative, say. Now, that's only one part of the story. That tells you that there is a zero there. That doesn't tell you that there aren't any zeros elsewhere. So like I can go up and I can say, yeah, I found 10 zeros using this intermediate value theorem method. That's great. But what about the zeros off the critical line? I should say our method, it's not just our method, everyone's method. There's no method that I know of that searches for a zero off the critical line. So our method only searches for zeros on the critical line. So if the Riemann hypothesis is false, then our method's not going to terminate. It's going to keep going around and around. So there's two bits to the puzzle. One, find me some zeros. And that's the Hardy Z function intermediate value theorem game. Two, tell me, please, that I haven't missed any. And that's a different thing. That's so rather than go into details, it's called Turing's method, Turing after Alan Turing. So then one has to say, can we get a Turing's method equivalent for these other functions? And yeah, people like Andy Booker wrote a very excellent expository article on that in experimental mathematics. So yes, more or less for any L function you like, so long as you get a Z function equivalent to find zeros and a Turing's method equivalent to say you haven't missed any, then you're in business.
Okay, all right. All right, thanks.
Sure, thank you.
Other questions?
Yeah, I've got one. So to make this kind of thing rigorous, you need to be doing this this interval method arguments, which means you need to extend the Hardy Z function to where you can take in an interval and give out an interval. And that means you need the gamma function and all kinds of other things also, all these different special functions. Is there a standard library that's emerging for that, or is everybody rolling their own solution?
Yeah, that's a good question. Certainly, yeah, you have all these special functions that you need to approximate. You have various Taylor series that you have to take out to 50 terms or something, and then truncate the error term exactly to find that you're definitely going to be within some interval. Now, I think the answer to your question is kind of yes and no, in that yes, some of the stuff that we used, and this is a classic. I mean, Canberra's the capital of Australia, so it's a classic political answer. I'm going to dodge the question. It's really a question for Dave. Why? There's some of the stuff that's in there is definitely pulled from a library, absolutely. Some of the stuff, though, we had to calculate, say, take 60 terms in the Taylor expansion, say, and then stop at some point and rigorously bound the error term and so on. And you know how it is, things like Stirling's approximation, which we can do to a higher degree of precision. So some of the stuff we had to do, but some of the stuff definitely was taken off the shelf. Now, I don't know what the proportion was of those things, but what better way to advertise the paper than to say the details should be in the paper?
So I have a sort of a simple-minded question. So if I understand what you said at the end, you've calculated the zeros of zeta on the critical line up to 3 times 10 to the 12th.
Yeah.
Any zeros off the line you wouldn't know anything about. But does this mean that there's a computer somewhere which actually has a list, to 5 or 500 decimal digits of the zeros on the line up to your maxima?
Yes, that's a good question. So let me just make sure that we're all on the same page. Yes, all the zeros up to 3 by 10 to the 12 lie on the line. And yes, just to flesh that out, we can guarantee there are none up to that height that lie off the line. We weren't looking for them. We were just looking for the ones on the line, but we had this Turing's method game that we could verify. Okay. So then the question is there some computer or some cloud sitting there with this data in it? Okay, so the short answer is no. All the zeros up to 3 by 10 to the 10, all of Platt's zeros, all of those sit in a 4 terabyte external hard drive in my office and in his office and in a few other offices around the world, just in case something happens to one of us. So we have these zeros on this massive hard drives. Now, for those who are interested, though, there is this website LMFDB. L functions and modular forms database, LMFDB, which should have maybe not the first, maybe not all of Platt's zeros, but maybe has all the zeros up to, I don't know, 10 to the 9 or something, to, I don't know, 1,000 decimal digits, say. So yes, there are some websites out there which will have zeros up to some height to crazy high precision. And there are some websites like Oditsko maybe maintains a list of, say, the first, I don't know, 100 zeros up to 5,000 decimal digits, say. I mean, there are some problems where you might want to say, I'm only interested in the first 10 zeros, but I want those zeros to 1,000,000 decimal places each, for example. It gets to a point where it's a bit tough for there to be so many websites for so many bespoke needs. So many people kind of calculate those as required. But yeah, there are algorithms around. If you want the first zero to 1,000,000 decimal places, that's doable. So Platt's zeros exist, and maybe not all of them, but a good chunk of them are on the LMFDB website. Now for ours, we didn't bother storing them because we wanted a difficulty storing that many zeros. So what we did, we would do a chunk of the real line. So say, I don't know, 3 times 10 to the 10 to 3.001 times 10 to the 10. And we'd say, find me some zeros in there. Great, I found 100. Do a quick check. Turing's method says I should find exactly 100. Great, I found them all. Okay, well now toss them out and move on. So we only, if you like, isolated them as far as we needed to. So we could say, yes, we found them. And yes, this is all we need. And so we can move on. So no, those extra zeros between Platt's original calculations and ours, they're not on file anywhere, no.
And how is your work related to the humongous calculations that Andrew Odlyzko had done many years ago?
Yeah, so, I mean, yeah, Odlyzko's calculations are Herculean and phenomenal and all the rest of it. I mean, one of his calculations, which we didn't do, one of his calculations was to say, okay, enough of this mucking around with zeros to low heights, right? With these zeta function games, probably the real order of things is like log, log, log t or something. So let's just go crazy high. Let's look at the zeros from 10 to the 100. Let's look at the first 100 zeros, say, after 10 to the 100. So we're not going to look at all the zeros up to that. It's too much. Let's just pick a random number and compute some zeros up to that height and do some sort of spot checks, some audits around these high heights. And let's look to see what are the distributions of those, because if we're going up higher, we might be getting closer to the truth in some vague sense. So those calculations are absolutely amazing, because what they show is that the higher you go, I forget the numbers offhand, but let's just say 10 to the 100, calculate 1,000 zeros around there. When you go up that high, you start to see that the distribution, which I completely glossed over in this talk, the vertical distribution, the gaps between the zeros, is more or less what you expect theoretically. As in, theoretically, we can predict with various models, random matrix theory, Gaussian unitary ensemble, whatever you want to call it, okay, various stuff, pair correlation conjecture. You can predict theoretically how the zeros ought to behave in the vertical distribution. They're all in the critical line, but how the vertical distribution is behaving. And rather remarkably, when you go out to this crazy high height and look at 1,000 zeros, say, it's like looking at like a black body curve or something. The data and the theory match up so well. It's an amazing calculation that is done. So we didn't do that. We could have done something similar to that. And part of me still hopes that someone, I don't think me because I'm running out of puff on this, but someone, it would be nice if someone took this 4 terabyte hard drive that Dave Platt and I have, and also stored at some other non-disclosed locations around the world. It'd be nice if someone took those banks of zeros and did some kind of proper statistical analysis on them, looked at the ratio of gaps, nearest neighbor spacings, and so on, to see whether that was also a good fit to the theoretical data, the theoretical prediction of the spacing between the zeros, how quickly that matches the numerical data. Now, it's one of those things where it's not a fun task to give to a student. It's the sort of thing maybe I'll give to a PhD student that I don't like. Maybe if a PhD student comes to me and I don't like the way he talks to me or something, I say, there you go, figure out this problem. But it would be nice to look at. So no, to answer in a roundabout way your question, we didn't try to do the similar sorts of things that Olitsko did. But Olitsko's calculations are so good, so from the 80s say, they're so good, or 80s and 90s, they're so good that if you like, you don't need any more. It's enough to give everyone evidence that the distribution of the zeros is following the same lines as these random matrix theory models, in that surely you don't need any more moral justification than that. You can see that, yeah, okay, now we, the community, should divert out some of our resources to people understanding random matrix theory and number theory, clearly, because there's something going on. So, yeah, in that sense, well, we didn't do it, but I guess we didn't need to do it in that the calculations were so good to begin with.
May I ask a question, or is that you're done?
No,
Okay.
go, please.
Yeah. So, how many copies of the 4 terabytes do you have?
Yeah.
And
At
so,
least-
and is it available? I mean, is there some sort of legal challenges to actually distributing it? I'm just curious.
Okay, so we have at least 2. I have one. Dave has one. Now, so every now and again, someone asks us. Someone says, "Hey, could I get a hold of your stuff?" And the easiest thing Dave says is, "Okay, like send me $80 or something, and I'll just get you a thing and email it and mail it to you." Now, but don't quote me on this, because it's been a long time since I checked the LMFDB database. Oh, sorry, the LMFDB. It's been a long time since I checked it. And I can't remember how many zeros they had put on from that data set. Look, maybe they put them all on. I don't know. When back in the day when we were mucking around with sending terabyte hard drives in suitcases and so on, and I was making sure that my duty-free whiskey didn't spill all over these zeros. No, it'd be terrible. So
You got yourself in that situation.
Yeah. So back in those days, there weren't that many zeros up on this database. But to be honest, I haven't checked it in so long. So that's maybe an exercise to the reader, is for people to see how many of those are up there.
Okay, so it wouldn't be a problem, for example, to throw it in the cloud or something like that. That's not a problem.
I think so. I think I yes, exactly right. And maybe they're already up there. You know, it's been so long since I've checked. But yes, I think that something like that would be possible. Yeah.
Okay, because you could do some cloud computing.
I could, yeah. I still don't really know what that means, but thankfully, I just handle the theoretical stuff, sharpening pencils and so on, and wearing ties. That's more my racket. But Dave handles the computational side of things. So yes, certainly, that's a good suggestion.
Other questions or comments for Tim?
I'd like to ask one final question, perhaps, if I may. There is the well-known theorem of Piatetsky-Shapiro that essentially gives a formula for producing primes. It's the greatest integer of something, pi raised of a number raised to some exponent. Now, that particular theorem it comes about because it's possible to nail down an interval of length less than 1, which must contain an integer, which must be a prime. So I was wondering whether perhaps you have some sense that the techniques that you have allows you to produce a formula that will guarantee the existence of an interval very high, and say in that interval there is a 0. I mean, not being able to produce the 0, but at least verify the existence of a 0 in a very small interval, very high up, by arguments similar to what Piatetsky-Shapiro did in his proof.
Yeah, it's a good question. So Pasch, in one interpretation of the question, I think the answer already exists. So in a sense, one way of interpreting Turing's method is to say, roughly speaking, is there a 0 in this interval, yes or no? Well, what I do, I find a few more zeros above it. It doesn't matter whether I've missed any, I find a few more, and then I chuck something in, and then that tells me, yes, the number of zeros in here is an integer. It's between 0 and 2, so it has to be 1, say.
Right.
So there are those kind of tools where you are using something which like happens to use the argument principle. Say you can bound the argument sufficiently well, so there has to be exactly the right number of zeros in there. So in that sense, that's partly embedded in the tools of the trade. But in another sense, if I say, yeah, pick some randomly large number like 10 to the 1,000, find me an interval around there where you can guarantee that I've got a zero. I don't, apart from quote unquote trivial things where you can say the zeros get closer together. So in a way it's cheating in that I could say 10 to the 1,000, plug in some trivial things. So between here and here, I can guarantee there's, I don't know, 1,000 zeros. That's 1,000 zeros in the critical strip. As far as I know, there's nothing that'll tell you that those zeros are on the critical line. So all these things are hopeless in the sense that all the techniques can't really distinguish. They don't have the eyesight to distinguish between 1 0 or 2 zeros close together on the critical line and 2 zeros off the critical line at the same imaginary part. Those things look the same at those sorts of scales. So trying to ask for a very precise result at some high height, I think, apart from kind of trivial stuff that you can say, is not going to lead anywhere. But yeah, the Turing's method is a way of saying I can guarantee a certain number lies in there. Yeah.
Right. Okay. All right. Thanks.
Sure.
Any other questions? If not,
Well, Mike, I would comment, of course, that method will work only if all the zeros are simple and you can separate them. Which algorithm, it does.
Yeah. So that's a good point, Jeff. Nice to see you again, Jeff. It's a good point. I said before that the method only works if the zeros are on the critical line. So as in, we're not going to find any zeros off the critical line. When we play the Turing's method game, it'll say, sorry, Tim, go back. You need to find 2 more zeros. And I'll look again. Didn't find any. Oh, sorry, Tim, if you go back and find 2 more zeros, I'll get stuck in this infinite loop. So not only will I not find a zero off the line, but also if there's a zero that's a double, say, and it's a non-separable zero, then I'm not going to find anything because all I'm looking for is sign changes. So more or less for free, I get out that not only are all the zeros that I found on the critical line, but they're all simple, say. I get that out more or less for free. So yes, you're quite right. The method is not going to detect zeros of multiplicity 2 or 4, for example. So yeah, that's another point considering, because yeah, we're just looking at sign changes of a function. Yeah.
Well, the method will detect. I mean, it will definitely detect if a double zero or if zeros off the line occur. It will detect that. It won't separate the 2 possibilities, but it will.
You're right. So the method, yeah. So it depends what we mean by detect. It depends what we mean by detect, because the method I describes in 2 parts. One is find the zeros. So I'm not going to find.
By detect, I mean you will be able to fault the algorithm, and you will have a proof that they're either a double zero on the line or they're zeros off the line below that height. You won't know which.
Yeah. But when I spit out a list of zeros, say, when I say, here are some numbers, the only numbers in that list will correspond to simple zeros. So in that sense, I'm not detecting simple zero, but just being colloquial here. I'm not detecting them. I'm only going to say, yes, I found a zero in this interval. And what zero was it? Well, by definition, it had to be a simple one. I'm only getting those numbers out because I'm only looking at sign changes. Yeah. Yeah, that's a good point.
Other questions?